Okay, excellent. So let me shortly introduce myself. I'm Jochen Landgraf from SRON and Space Research Organization Netherlands. And I would like to talk about radiative transfer theory. And I know it's one of your last days, isn't it? Of the summer school. And you know, it's really about theory. So I can only give you some ideas about that theory. It started actually with people like Kepler, so centuries ago, and this theory evolved in course of the time. So why does it make sense to talk about that theory today? I do believe that you have heard already something about satellite observations, right? Maybe some data you've seen from Traboni on Sentinel-5 precursor, so Sentinel-2 in the presentation just a few minutes ago. I think there was also a course on the polarimeter, measuring aerosols. All these instruments, they do measure radiation, right? That's the only thing that we can measure. And so you get the radiation information of that, and you want to get some information out of that, information out of a spectrum, for example, right? And so you need a model which simulates that observation, doing some assumptions, for example, about the composition of the Earth atmosphere. And then you see a model and observation, you do not agree, you adjust your assumptions, you try to bring them into agreement, and then you think, this assumption I made for my simulation, those are the correct assumptions. So you need a model to simulate the method observation. And this is something you can do with the radiative transfer theory. You can develop a model that simulates the transport of radiation through the atmosphere. And that's why it makes sense to talk about it. Another reason is it's my personal passion. I started to work on radiative transfer theory already during my PhD, and I got the task to simulate the amount of radiation available at different places on Earth. Why? Because radiation, particularly in the ultraviolet and visible, gets absorbed by molecules, they break up, they totally dissociate, we call that, they form radicals. And these are radicals, they trigger the chemical reactions in the atmosphere. So if you want to simulate that, you have to know how much radiation. And one big problem I had to focus during my PhD how can we now go further? Extremely. Anyway, one task, one aspect which made my life difficult, those are clouds. Yeah, those clouds, they really change radiation above the cloud, it's bright, below the cloud, it's very dark. So I had to simulate that, and I found always in my simulation a lot of radiation present in the upper few meters of the cloud, the distinct peak. And so I developed this model, and I thought, you know, I don't know if you've ever worked with a model. Most of your time you're debugging, you're trying to find the bugs. And so I thought, the great thing was that I think it was a month later, I took a flight from no work, I left from Frankfurt, and we crossed stratiform cloud layer with the aircraft. I had a window seat, and I looked outside, and I really saw that when you really reach the top of the cloud, it becomes extremely bright. You see light coming from all directions. And I found that fascinating. I worked on a theory, and I combined them with an observation, a simple observation, just looking out of a window, and I could bring them into agreement. So a theory which is pretty close to our visual sensing on a daily basis. I really was extremely happy and followed that theory then till today.
We also have a pointer if you would rather.
Yeah, pointer here.
Okay. Is that?
Oh, that's a fancy man. Yeah. Another thing why we want to learn something about radiative transfer is illustrated here in this animation. If you're an astronomer, you observe objects, right, on Earth. This light traveled years, if not hundreds of years through the universe. And we measure these photons here at Earth. And these photons, they tell us something. They tell us something about the source, maybe a star, maybe a nebula that crossed. And so the photon, light in general, is a messenger. Is a message which tells us a story. And the task we have is to unravel that information, to get it out of the spectrum. And therefore, you need radiative transfer. You have to simulate the life cycle of a photon from birth, life, to death. Death is finally our observation, right? And I want to give you a few examples. Do you remember this one? That is Sentinel-5 precursor. The Dutch people are extremely proud about that mission. It was a great success, launched about 7 years ago. I think you've heard about nitrogen dioxide measurements, maybe even the greenhouse gas, I don't know. So what does this satellite actually do? It flies around the Earth, looks downward and measures the light reflected by the Earth. So that light went through the atmosphere, and there it interacts with molecules in the atmosphere, scattered, it's partly absorbed, and then it's reflected at the ground, and then goes to the satellite, and then in the instrument we have this process element, we measure spectrum, and we try then to analyze the absorption features we see. That tells us something about the atmospheric composition at that glacier on Earth. So that's the basic idea. So we need to simulate the transport of radiation through the atmosphere in this case. If you're not a satellite guy, maybe you're more interested in ground-based measurements. These are typical instruments you find at many universities, also in the Netherlands. I think that is a photo from Japan, if I remember right. A ground-based measurement. They look to the sky, measure maybe the direct sunlight, and try to determine in that way something about the Earth atmosphere. For astronomers, the Sophia experiment, maybe you've seen that. It's a spectrometer on the aircraft. There's a joint collaboration between NASA and DLR. You can open the aircraft, you can point to the sky, and then observe the light. Again, if you want to interpret that, you need to know something about transport of radiation. So you may say now, Jochen, what are you telling us? There are so many theories which already describe interaction of matter with light, right? I don't know if you have followed studying physics. I think you had followed a course electrodynamics, right? What is that about? Solving the Maxwell equation. And the Maxwell equation, they tell you something about interaction of light with matter. So the theory is very amazing. Even if you're more advanced, you went to the quantum theory, quantum electrodynamics, which is really a tough one. I understood it partly, but really that is the most fundamental theory we have. So why radiative transfer? You know, if you try to simulate this quantum electrodynamics, which you see looking outside of the window, you have a job you can't solve. It's too complex, right? So the theory is fundamental, but it's very limited in its daily application if you want to simulate an observation, right? So we need a theory which is, in its basic assumption, more simple and gives us a much broader field of, so that we really can simulate an observation when we have a satellite pointing out of the city. So that is why we need radiative transfer. When you develop a theory, so I think you are one who has to develop a theory, then you need first to know what you want to simulate that, what field you want to do, right? In electrodynamics, it's the electromagnetic field, right? That's what we simulate. In quantum theory, it's a wave function that describing the probability that an electron somewhere showing up, right? What is our field then? That is what we call the radiance. And the radiance is nothing else than an energy flux through a surface. So it's a function at a certain position, x, and we have an energy flux through that surface, A, of light, which goes in the direction omega inside a solid angle d omega. So it's nothing else than this definition here, the energy measured per time the area, that's the flux, per solid angle in a certain direction, and also limited in spectral dimensions of per wave. So that is our field, right? And it's the corresponding quantity to the electromagnetic field in active dynamics or basic function in quantum theory. The funny thing about that quantity is that we cannot measure it. It's a very ideal quantity. So we need a recipe whenever we have these radians simulating the electricity. We need a recipe to translate that to an observation. And that can be, for example, for a spectrometer. It's just an example. That translation of how we simulate the observation depends on the instrument. And having such a spectrometer, which measures light within a certain opening angle, certain wavelength range, certain opening pupil size. So it is then the integration about the pupil size, time of observation, the spectral range the instrument is sensitive to, and the opening angle of our instrument. So we integrate the radians of a certain range, and then we finally get our observation, and that we can compare with what our instrument is. So just going many steps now ahead. So we need the radians, and what you need then is an equation that you have to solve to get that radiant field. Like the Maxwell equation, electrodynamics, the Schrödinger equation, quantum mechanics, and we do have now this terrible equation here, which we try to understand in the course of the next few minutes. And the only thing I want to say here is, look at that equation. It includes the radiance field here, I, at this place, at this place. It's a kind of differential equation, a bit more complex, not only a differential equation, but that is the equation we have to solve. And what we will do now is we go through the different terms and try to understand it. And how do we want to do that? We just follow this simple recipe. The birth of a photon, its death, and its life. And going through these different aspects of the life of a photon, we will learn more about radiation. Yeah. Who knows Planck radiation? Ever heard about Planck radiation? That's pretty good. So, what is the concept there? It goes really back to the beginning of last century. Big discovery. If you have a cavity given here in black, that's matter, right? Whatever matter is. And that matter has a certain temperature. And matter has the property that it emits and absorbs photon continuously, right? You have these two aspects, the birth and the death of photon. And if the cavity is closed, you will get an equilibrium inside your cavity, a radiation field, because of the continuous emission and absorption of photons as an interaction with matter. And the thing is about that radiation field, it's a big question. How does it look like? What is the frequency distribution, the wavelength distribution of that radiation field? That was the question beginning last century. And the funny thing is that this radiation, which you do have in just a cavity, in that equilibrium, only depends on the temperature of the cavity. That's the only property of matter which determines the radiation. They wanted to find out how the radiance looks like in that cavity. And you now say, oh, the cavity. But this is a symbol for all interaction of matter with its surrounding radiation field when it is in equilibrium. So if you go locally in the atmosphere and you look at the radiation field, say in the infrared, matter, the gases behave similar as the cavity. The matter is in equilibrium with the radiation field around it, right? And then it was Planck who solved that puzzle. He made some assumptions and said, hey, this matter, what is the, at that time people thought about oscillators, charges, and he said, in that matter there are charges, linear oscillators, and they vibrate, and the energy levels this can have that is discrete. Normally, if you have an oscillator, it can have any energy, because you have to vibrate a bit faster. But he said, no. that doesn't do it. We have to assume that these oscillation of charges and matter, they only exist at certain discrete energy levels. E naught, the ground state, E naught, that's the first excited state, and so on. And using that assumption, and this assumption that there's an equilibrium, thermodynamic equilibrium, he could derive the Planck radiation. That is the radiance in the cavity. And it only depends on temperature as a matter property and describes us how the frequency distribution is. And that's what you see here on the right. Those are the famous Planck curves. And I think he got the Nobel Prize for that, probably not only for that, and other discoveries. And what you do see is, as a function of wavelength or color of light, how much radiation is available. And the different temperatures. And now look at the 300 Kelvin. 300 Kelvin corresponds a bit to the surface temperature we have, right? And it has its maximum at 10 micrometer. Do you know what the 10 micrometer range is in the Earth's atmosphere? Did you hear about the atmospheric window? Right? What's the atmospheric window? Well, the atmosphere is transparent, right? So light can escape through the atmosphere into empty space. And that's very important that we have that window because it balances the radiation our Earth receives in the visible near-infrared from the sun. We receive energy, and we have to get rid of it. We get it rid because of the Earth's surface, which emits radiation of 300. We now make a step forward in our understanding of matter and what it does with radiation. And the birth of a photon, and I'm pretty sure you all have seen that thousands of times in your life, is nothing else than you have a molecule or atom in an excited state, and it falls down, does a transition to the ground state, and it emits a photon of the energy difference of these two energy levels, right? That's a bit straightforward picture using Einstein, which came up with the relation that the energy difference can be translated in frequency. With h nu, the frequency, we can even calculate the wavelength of the emitter. Yeah, that's straightforward standard physics. So, what do we do with that model? We assume now that we have a small volume, and there are many, many molecules with these two energy states in it. And two molecules or particles are in the excited state, and one in the ground state, and the total number of particles is constant. So whenever a particle goes from the excited state to the ground state, you get one less in the excited state, and two gets one less, and we gain one in the ground state. Makes sense, right? So that's a basic assumption here. And now we look at different processes in which such a two-level system can go through. And that is a more detailed picture. So we talked about emission, but we can also have absorption of light. So where the molecule goes from the ground state to the excited state, and it absorbs the photon, right? That's the test. We also can have what we call stimulated emissions. That means that the molecule is in the ground state, the photon comes by and has the energy, or the gap that we do see here, and the molecule is in the excited state, and it hits one of these photons, and what it does, it emits two coherent photons. So it's a kind of birth of photon, yeah? And last but not least, spontaneous emission. This molecule remains in the excited state, and at a certain time, it's the end of its life, and it falls spontaneously back into the ground state. Continuously. You can only understand that, by the way, when you study quantum electrodynamics. But the important point for us is that if an energy state has a finite lifetime, the energy definition becomes fuzzy because of Heisenberg. Heisenberg said, if you have the uncertainty in time of a state, its energy is also uncertain, and it must follow that relation. Delta T in time times delta E in energy must be larger than a certain quantity. So the longer a state exists, the more sharply the energy level is defined. The shorter, the more fuzzy it gets. And the fuzziness of this excited state can be described by this function. It's a Lorentz line shape, and so it's a kind of function which has its minimum or minimum at the exact energy level difference that we see here, and it's a bit fuzzy, having rings to the left and to the right, and this depends on the lifetime. So now I want to show you something which I find quite surprising. I won't go through the math, because the math is given in the material for this lecture. I don't want to do that today. I just want to tell you the story behind it. Yeah, and I find that quite fun to say. Assume that we have now a volume UV, and we look at what happens with the light along a small distance ES, right? And there's some material in it. It's at least n particles, and 1 in the ground state and 2 in the excited state. We assume that this matter is in equilibrium with radiation, and then Boltzmann was the guy who told us if that is in equilibrium, there's a kind of distribution between molecules in the excited state compared to the one in the state, the Boltzmann distribution. So we use that, and then we look at the gain of light, or loss of light we get along that little distance. And then we can calculate the loss of light because of absorption, right? Absorption is the death of the photon. We get a loss rate, but we get also a gain rate. We gain photons because of stimulated emission, and we get a gain of photons because of the spontaneous emission. And if you do that very carefully and you do all the math, you end up with the first version of our rate transfer equation. You only have to make these assumptions, and you end up with something fascinating. The rate of transfer equation in this form, the change of the radiance along a small distance ds is proportional to the radiance itself with what we call the extinction coefficient. The extinction coefficient describes the oxidative properties of the matter. It's a larger number, a lot of light is absorbed, it's a small number, it's a little light absorbed, right? And then we get another term, and that is the gain of light, and that is because of the Planck radiation that we have along that light path. Photons are emitted, so we do get a gain. So it's a differential equation. We do know that quantity because Planck told us how that looks like, and you can try to solve that equation. When we are interested in matter, we have to talk a bit about this extinction coefficient, because that describes the optical properties of the material the light goes through. And doing the analysis, you can show that this coefficient is proportional to the number of particles in our volume. That makes sense. The more particles, the more light gets absorbed, right? It also says that we have what is called a microscopic absorption cross-section. It's something which describes how light is absorbed. And the theory says that this absorption cross-section is a quantity which says how strong the absorption is, that is S, the so-called line intensity, and a profile. And this profile, shown here, that is an absorption line, and it has a certain shape. And that remembers you what I said about the fuzziness of the energy level because of the spontaneous emission, right? Because of that, the light is not only absorbed at a sharp wavelength, but there's a kind of uncertainty because of the fuzziness of the excited state due to the spontaneous. Very narrow line. Yeah. Sure.
Can you remind me, how does the microscopic radiative transfer equation relate to the not microscopic radiative transfer?
Not microscopic. I have no clue what not microscopic actually is.
Okay.
It's always a microscopic description, and I want to stress that.
Oh, okay, sorry.
Yeah.
I thought we were heading into a new.
No.
Okay, good.
No. That is the first part of our transfer
Okay,
equation
yeah.
I showed you already.
Oh, right,
Yeah.
okay, sorry.
It's a bit more complicated. Other terms will follow.
Yeah, okay.
But okay, yeah. But important is this line shape which already comes from that field. Now we go ahead because we do know that quantum mechanics tells us a lot about absorption features, about energy levels of molecule. We have to recap that a bit, right? So we followed a bit of the classical theory using Planck, and now on top of that, we use now more information coming from quantum mechanics to specify these absorption processes. So rate of transfer gets its information from the left, from the right, you know, combine that as an input, and then tries to solve the rate of transfer. So the death of a photon, and we talked about these two energy levels. That was the picture so far. But you remember, I'm pretty sure, already at school we learned about the Bohr model of an atom. That there are electrons circulating around the nucleus, right? And here's the picture of an atom. And it's a good picture. It's not so bad, you know? So we have the nucleus very dense in the center, and the electrons, they are in certain orbits, and there's a population density, and those orbit 2 and 8, we all know that. And this transition that we showed here is actually a transition mostly of an electron in the outer orbit going to an excited transition. Those are these two levels we're talking about. So you may say, oh, we're done. Good, yeah. Unfortunately, in the atmosphere, we have more molecules and not atoms. And a molecule is a bit more complex. It has not only one nucleus, but 2, 3 nuclei. And they react to the radiation as well, right? For an atom, we call that an electronic transition because the electrons make the transition and the nucleus doesn't care. But for a molecule, it's a bit more complex. And I just want to summarize that because then we understand a bit how this absorption spectrum actually works. So we have a molecule, 2 nuclei, which we see here, and then those are the orbits. So that gives us the probability that the electrons are at a certain location. And then there's the electromagnetic light, which comes and hits that molecule. And what it does, it not only interacts with the electrons, but also with the nuclei. So the transition that we have to consider is the transition of the full molecule, not only of electrons. And that's what we do see in the absorption. The molecule goes from a ground state to an excited state. So we want to solve the Schrödinger equation for such a complicated system, and I can tell you, strictly speaking, this is impossible. You need approximation. I mean, even if you ever try to solve the Schrödinger equation of the hydrogen atom, this is already difficult. This is simply impossible. So you need smart guys to come up with approximations. And I want to mention here 2 of them, Max Born and Oppenheimer. But Oppenheimer, for sure, you know. And they found a very smart approximation, which is quite based on basic assumptions on kinetics we can all understand. And that is something I want to explain, not how you solve the Schrödinger equation. You can have a look at in the material, they're sketched a bit, but there are books describing that as well. So what happens is that we say, hey, these nuclei, they are so much heavier than the electron. The proton is 2,000 times more heavier than an electron, right? And a nucleus, you can imagine, much more. And now think about kinetics. They have these heavy nuclei, and you know, they behave very slowly. And around that, we have the light electrons, very agile, running to the left, to the right, whatever, right? Having that picture in mind, it makes sense to say, okay, let us first consider that the nuclei stay where they are, and only consider the electron. And as a perturbation correction on top of that, we then describe how the nuclei react to the radiation which comes in. And that is all That's the basic assumption about the von Oppenheimer approximation and the math test, right? So we have to think of the electronic transition. We understand already a bit, so the electrons go from one orbit to the other. But what happens with the nuclei? The nuclei here, two nuclei, let's say that's oxygen in the atmosphere, O2, or nitrogen, N2, and they can vibrate, right? Yeah, the nuclei, and they can just vibrate them as a linear oscillator. For sure, we could want to have a conversation related to that. We have our oscillator with a different energy level. So that is one motion of the nuclei that we have to consider as a correction to the electronic transition. Then we have the rotational movement of the nuclei. So they can rotate, and this needs also quantization, and describes then the different energy levels. So we have electronic transition, the electron jumps from one level to the other. We have the vibrational one, and we have the rotation. Translation energy is not important for them. And when you look now at the energy levels that we have to work with in real life, it looks like on the right. It's not only two levels, but we have the electronic transition over there. Yeah, the electron goes from a lower energy to a higher energy level. Light related to that transition is in the visible, the ultraviolet. Then we have the correction, the vibrational transitions, because of the vibration of the nuclei. So those are these levels over there, right? And then on top of that, tiny corrections because of the rotation of the nuclei. Vibrational transitions, so when we go from one vibrational level to the other, they are in the shortwave infrared, 1.6 micrometer, for example. I will talk in a second about that. And the vibrational line is sub-millimeter. Actually, standard spectrometers, you can't measure this. And for sure, not all the transitions are actually allowed when you calculate the probability of that transition of a molecule. So there are some transitions which are not allowed, or many actually, for the CO2 molecule, for example. You can use symmetries of the molecule. It's a linear molecule. So there's a symmetry in the molecule, and when you look at that, you can smart people can say then the transition probability must be zero, otherwise you violate the symmetry. Yeah. Having said that, I want to give you now an example. That's a famous spectral range for people working with satellites, the 1.6 micrometer band, and you can retrieve from that carbon dioxide for the most important thing. And you do see here now groups of absorption lines, right? So let us first consider this group here and this group. Those are transitions from one vibrational state to the other. Electronic transitions are not allowed for CO2. That's why we do not see CO2 absorption lines in the visible. We have to go to shorter wavelength, and then we see these two groups. Then we see the individual lines, and those are, when we go back, transitions from one vibrational level to the other, starting from one rotational level going to another, right? And because there are different options, you can go here, you see these individual lines grouped as seen in this figure. So that's a story, that is a spectrum. And you may say now, each line is not a single sharp delta, but it is a profile. Yeah? We already talked about that. Which is partly true, but for atmospheric application, this line shape is too narrow. There are other processes in the atmosphere which determines actually the line shape of these individual lines. And I want to give you a bit of an idea which processes determines finally the width of these individual lines.
What is the small bump? So you have two clusters, and then you have also a dip in the middle. What's that about?
Okay, these are all transitions where the rotational quantum number changes by +1, and those are those but they change by -1, or the other way.
So at 0, it's more stable or
Yeah.
something.
Sorry, on that x-axis, what's that scale? How many like
That's
nanometers?
wavelength.
Yeah.
It goes from 1.59 micrometer to 1.68 micrometer. It's a typical band that can be observed by satellite instruments. And because that is my home base, I choose that. And by the way, one mission I'm working now on really only focus on these bands. So you really want to derive greenhouse gases from this absorption.
Which mission?
Tango called. Tango. Do you know it? Never.
I work at the UNL, so I'm gonna work on.
Oh, then you know that. Then you know Tango.
We have also
It was also
yeah,
mentioned in
it's-
some
in some presentations they mentioned.
Really?
Yeah.
Cool. Yeah, I'm the PI mission, principal investigator at Tango.
KNMI mentioned it.
Yeah, a couple of presentations.
SRON
Yeah.
mentioned it, and then also the
Nice to hear that.
You're very popular.
All right. So I want to show you now two physical processes which cause the width of these lines in the atmosphere, which is not the lifetime. So the lifetime, the related width of the line is too narrow for classical effect. And the first one is called pressure broadening or collision-induced broadening. And therefore, I want to start with that little movie which shows a microscope and some bacteria. And you see the bacteria, and now they zoom in, and you see the bacteria jiggling around. Yeah, they move a bit, kind of erratic movement. That is the Brownian motion. You may have heard about that. You know where it comes from? It's not that the bacteria itself, they think, oh, now I go a few micrometers to the left or to the right. That's not what they do. The reason is the movement of the molecules, which you can't see. And that is shown on the right. You see the bacterium in blue and the molecules in red, they hit the bacterium. And because that is a kind of random walk they do, this bacterium, that is these molecules, they hit the bacteria sometimes to the right, sometimes to the left. Right? So the basic thing is molecules, they move, right? They're continuously moving. And they do not only hit the bacterium here in the picture, but they also hit themselves. And if a molecule in the excited state hits a molecule in the ground state, the molecule goes immediately in the ground state and emits a photon. So the lifetime gets reduced by collision. And that causes a widening of the absorption line because the energy level becomes more uncertain. Right? So that is collision-induced broadening, and it happens mainly in the lower part of the atmosphere. Because there the pressure is highest, the density is highest, and the chance of collision is high, right? Very interesting. The next one. Oh yeah, here you see an example of a line. I think, I'm not sure, I think it's also a C2 line somewhere in the spectrum. And you see the different pressure levels. So at 200 millibar, 200 hectopascal, which is about at 12 kilometer. Density of air is low, the line is pretty narrow. Right? That's the blue one. And when we calculate or observe the line at the pressure here at surface, about 1000 hectopascal, you see the broadening. And now you can imagine that these lines, they get broader and broader, and they mix each other, they interfere with each other. So this needs to be accounted for. Yeah.
That's at its temperature rise.
Yeah, that's it. Temperature also has an effect. The second effect that is also pretty funny. Everybody knows Sheldon and the famous costume, right? I got it from my son. The Doppler T-shirt I had. The Doppler effect. And now think of the physics of absorption must be described in the molecule reference frame. So a reference frame which moves with the molecule, right? But in the lab, we have our light source, lab frame, and that has a certain frequency. Depending on the speed of the molecule sees that light by a different frequency, right? That is the Doppler effect. And now it is that in thermal equilibrium, as we do have outside, the speed distribution of molecules is described by a famous distribution function. and that is the Maxwell-Boltzmann distribution. And when you know that, you can calculate the plotting of a line, because each molecule sees the frequency of the light slightly different, right? So that is the Doppler plotting of light. And that's particularly important when you go up higher in the atmosphere, so at, say, 12 kilometers. I come to the, just have to check the time. I have to speed up a bit. About scattering. That's the life of a photon. Right? We had the death, we had the birth, and now the life of the photon. And you may say, scattering, that's like snooker, right? The molecule, photon hits, gets reflected, but that's not true. It's more complicated. And we need now again another theory which describes scattering, and we use that then in our rate transfer theory to include that. How does that work? Again, only at top level, yeah? We have to go to the electrodynamics. We have to solve the Maxwell equation. So light comes in from the light. It's plane wave, light oscillates, and you have here a particle, and that light induces in the particle the charge distribution, which changes because of the oscillation of the electromagnetic field, right? And because there's a change in the charge distribution, it emits radiation, like an antenna, right? And what we finally have to do is we have to calculate the electromagnetic field, which is scattered, and must interfere that with the incoming field. So there's interference happening between the incoming light and the scatter light, and that determines finally the scattering distribution of the particle. So we really have to go into the Maxwell theory. We have to solve here the so-called Helmholtz equations, and that describes as the property of the electromagnetic field. And then we need the link of the electromagnetic field with the radiance, and then we can describe a scattering in our wave transfer field. And exactly this is what we do. So what we do is, in the wave transfer theory, we have to link that's a schematic scheme of scattering. Incoming light, radiance, is scattered there in this direction. And we describe that by the simple relation. The intensity of the incoming, or the radiance of the incoming light, is related to the scattered radiance in a certain direction. We have one quantity, which is omega naught, which in the scattering medium is important, that describes the probability that the scattering event really happens, right? And then there's another function, the phase function, which describes that this is happening in a certain direction. You can combine it with one quantity, it's bits, you know, that's how we do it. And we calculate now this quantities from the Maxwell theory. And that goes into the rate of transfer in the sense that we say, what is now the change of light along a small distance here? It can be scattered from all different directions and can contribute to light in the viewing direction shown here. So what we do is we integrate the phase function over all directions with the radiance coming from all directions. We multiply it with the probability that the scattering will happen, and that gives us the light in a particular direction. That is called the source term, and that's an extra term we add now to the rate transfer equation. And we are there, we have our rate transfer equation, right? The change of the intensity along a small distance, that came from the Planck theory, the attenuation term, the contribution because of Planck radiation, and the contribution. The only thing is that you have to solve that equation, which is extremely difficult. Because it's not only a differential equation, right? It also has the radiance in the integral hidden here. That's why we call it an integral differential equation. And there are methods to do that, but we won't discuss that. That's math, right? I just want to give you one example how that works with the scattering. That is Rayleigh scattering. You know, who knows Rayleigh scattering? Good. Good. What happens? The electromagnetic wave hits a molecule, or like NO2 or O2, which is pretty small compared to the wavelength. That's important. And that introduces a dipole moment, which oscillates. You know, the electromagnetic field oscillates, and then this dipole also oscillates. The charge distribution in the molecule. And that's an antenna. And it was Hertz who derived how the scattered electromagnetic field looks like. And we can use now the solution of Hertz to do that. And so we have the scattered electromagnetic light. And now we can calculate from that, if we go to a theory, Stokes vector you have to calculate, we can calculate the scattered radiance from the solution coming from Maxwell, from the Maxwell equation. And what we then get is what we call the scattering cross-section of Rayleigh scattering times the Rayleigh scattering phase function, which is shown here. That is, this light comes from the right, and that describes the probability of scattering. So most light is scattered forward and backward. We have a minimum in the perpendicular direction. That's not so important for Rayleigh scattering. Probably you know more the scattering coefficient, which is 1 over lambda 4, right? So lambda is the wavelength. So if the wavelength is small, you have a lot of scattering. If the wavelength is long, then the scattering is extremely weak. And that is why the sky is blue. We have an observation. We look upward, we do see scattered light by molecules, nitrogen molecules and oxygen molecules in the atmosphere. They are so small that they do Rayleigh scatter. And they prefer to scatter blue light and much less red light. If you look at the scattering cross-section, the ratio between blue and red here in wavelength is a factor of 8, right? And that's why the sky is blue. And that's also why the sunset is red, because blue light is scattered away, and the only thing that remains from the sun is red. So that's the story behind it. So light is not snooker. It is more complicated. We have to go to the Maxwell theory and feed that into the I want to use the last minutes to explain shortly what we can do to solve that equation. And I have to speed up a bit. You know, this equation is quite complex. What I want to show you now is a very simple solution. And what we do first is that we assume a flat Earth, we say a plane curve atmosphere. We also assume that in the horizontal, everything is the same, homogeneous, there are no variation. We further assume that thermal radiation can be ignored, so no blank radiation, we are say visible, and then the temperature is too low that we get blank radiation, and scattering will also pass. So very strong simplification. But with that, we can do something. We can, and maybe I want to skip the math here a bit. We can simply, because the scattering term is not ignored, we can integrate the rate of transfer equation. A simple integration, right? And what do you expect to get? Forget the math here, because I have to jump now a bit further over. We get simply the absorption law, Lambert-Beer's absorption law. Ever heard about it? No? So if we do so, and I added this one, we do get that as a solution by integration. That if you consider a line of sight, and we want to, when we know the radiance at position R0, and we want to calculate it at the position R1, it's simply the radiance times the transmission function, where we have in the exponent the optical depth of the atmosphere becomes the transmission function, right? And it's called the Bouguer-Lambert-Beer's absorption law. And I was a bit quick here because these three names, there's a great story behind that. And I really want to tell you that story before we start. It really goes back to the beginning of modern science. And the first name I want to mention that is Kepler. You need to understand Kepler, what he found. And he said, if you have a point source of light and you look at the energy flux through a surface R, and you compare that to the energy flux through the same surface at a distance, twice the distance, the energy flux goes down by a factor of 4. And the same you can do with 3 times the distance. And in general, he said, what happens is that the energy flux behaves inversely proportional to the square of the distance, right? Which is quite obvious when you look at the picture. Yeah? That is a very important thing, and Bouguer knew about that, and he made a famous experiment. And and you look at that, how smart this guy was, it's unbelievable. Because they didn't have a modern lab, right? So what he had is, oh, it's dying. Yeah, you see one, you find it. Also dying. Okay, doesn't matter. That's the observer. There's a candle, and there's some optical material, a block, right? And he observed the candle via that material through a mirror, right? And then we changed the amount of material in the yellow light path, 2 blocks, 3 blocks, 4 blocks, and so on. And for sure, the candle got darker, right? But he had now to measure how much darker it got. And therefore, he did a reference measurement, going not through material by a second mirror observing the candle. And he could change the distance. And he changed the distance that the candle had the same brightness looking through line yellow and orange. Measuring the distance, he could say how much the intensity got reduced, right? I find that fantastic. I'm really, and that is from his original publication. He couldn't quantify it in terms of absolute numbers, but here you see how the radiance decay as a function of adding material. So that was the start of that law. And then Lambert became a mathematician. He knew the results and could translate it in equations. And he came up with that equation where he said, okay, the more material you add, we have to add the transmission factor to describe the attenuation of light. That was his contribution, right? But he only said there is some attenuation coefficient in the exponent. And then it was Baer, years later, who made another experiment shown here, the same principle. You observe one to the left and one to the right. The left, a light source here and there, and you have a gas cell in between. You can change the distance as Doge did as well, but now in a well-coordinated way. And he changed the concentration of something in the cell, right? And tuning that with the distance and checking how much the light got attenuated, he found that the attenuation coefficient is a quantity sigma, which is the absorption coefficient we already talked about, times the density of the material in the cell. That is the history about this. So if you now want to understand more about that, how we apply that in the atmosphere, typically a model is like that. That we have a sum, and we divide the atmosphere in layers. We specify the optical property per layer, the extinction coefficient. We calculate the optical thickness along that line of sight. Then we can calculate how much light is at the ground. We can do that on the computer. Now we have to assume how much light is reflected at the ground. That is the so-called Lambertian albedo. It's just a quantity which describes the brightness of the ground. Then we go up the same way, calculating the attenuation for all the layers, and finally we have our light at set, right? You can also do that for ground-based measurement, then you have to stop here, right? That's quite simple. Yeah. And now I want to show you a final result of such a simulation. What do we see here? We do see in yellow the sun as it illuminates the atmosphere. It can be approximated by a Planck curve of 6,000 Kelvin, also a body radiator of high temperature. And the yellow one is actually measurement. Then in red, we see the simulations at ground level. First, we see that there's a difference, particularly at shorter wavelengths. Here's the visible, right? And that is mainly Rayleigh scattering. This light is scattered out of the line of sight. But we see also absorption features like the oxygen A band, the water vapor absorption. The more we go to the longer wavelengths, the closer they get on top of each other, because Rayleigh scattering becomes less important, right? So in the 1.6 micrometer, my favorite band, they are on top of each other. But you see these tiny wiggles. And those are, on that resolution, you see 2 absorption capacities, right? So a very nice figure. And with that, I'm at the end of this short lecture, you know, you could spend your whole life on radiative transfer. It's a fantastic theory because it combines different aspects: thermodynamics, electrodynamics, quantum mechanics, and then the solution and the work and working with computers. I really love it. What I want to say is that this theory got really a push with the advance of modern computers, because you have to solve the scattering in the equation of a computer in a numerical way. Yeah? And that's what we do. You can even expand the theory to describe polarization. Then you have to look at not only the radiance, but other quantities. So parameters there called IQ and U and V. And if you talk about an instrument like SRON, then you have to do that. Right? And last but not least, is the radiative transfer theory perfect? No, it isn't. There are situations where we do know that the whole concept fits. Yeah, that's a certain geometry. It's called the current backscattering, where we cannot use the radiative transfer theory at all. And then we have to find different ways to simulate that. And with that, I want to close this lecture. I hope you get a bit of a feeling what kind of work is here behind. And maybe in your life you will one or the other have to do the radiative transfer. Thank you.